What I have here is the infrared receiver circuit I designed using the simulation software. The intention here is to build a proximity sensor for my Raspberry Pi robotics project, the robotics vacuum cleaner. I need at least 4 of the sensors to be installed on the sides of this vacuum cleaner for side sensing. I spent so much time on the internet downloading some circuits and looking for infrared transmitter and receiver that I can use to build the proximity sensor. However, none of the circuits that I downloaded works properly. Some even didn't work at all. So I decided to build it and to design it myself. Unfortunately, at first it didn't work. But according to the simulation software, the circuit here I'm showing you works properly. But in real life, it didn't work at all. I have no choice but to find out exactly what happened, what goes wrong, why the circuit didn't work. Contrary to what I've said a while ago, the circuit worked the other way. This relay here is always active, causing the current to be drained from the power source. So it's not good since I'm using a battery. I need to disable this relay if there is no infrared signal present at the input here. By the way, this signal generator represents the infrared module. So what I did is to check all the signal points why the relay is always active. So I'm in the point of removing all the transistors and begin all over again. Fortunately, by tracing all the signals at the signal points using the oscilloscope, I was able to identify what's wrong with the circuit. The amplifier must function as an inverter because the 5 volts is always present when the infrared module here is always active. If the infrared module is not active, a 5 volts always goes to the input of these transistors. Normally, this infrared module outputs low when there is an infrared detected at its input. Here is the actual circuit now. As usual, I fabricated my own circuit board. Here is the outcome of my after the modification. Originally, this bias resistor is 560K. So I changed it down to 560 ohms. But this can be changed from 560 ohms to 750 ohms. This 5 volts regulator represents the infrared module. It outputs 5 volts if it's not active. So the grounding represents that the infrared module is active or the output is low. This is the modification, which is quite unorthodox. Originally, there's no connection between the base of Q1 to the diode cathode D1. So after creating this short, it gives an indication that the circuit is going to work. Now I'm going to show you the actual simulation of the circuit. Right now, as you can see here, the circuit is supplied with 5 volts. Supplied with 10 volts. And the infrared module is not active or not receiving any signal. You can see here that the resistance of the relay is almost infinite, and the supply is 10 volts at the collector of the output transistor. I changed over the switch to ground to simulate the infrared module is now active or receiving an infrared signal from infrared transmitter. As you can see here, it's dropping down now to 0 resistance, to 0 ohm resistance. And the voltage now show that there's a voltage drop across the relay, indicating that the relay is now engaged. And you can see here the circuit is closed at the output of the relay contacts. And the LED here is showing an orange light. Unfortunately, my camera cannot sense the orange light here. Again, I cut off the circuit switch. This revert back to high infinite resistance and to 10 volts. By the way, this is only the receiver part of the proximity sensor. You can use any commonly available circuit for infrared transmitter using the 555 transistor. Now the actual circuit. I set the power supply here to 9 volts and it's supplying about 90 milliamps to the circuit board. As you can see here, if I put the object in front of it, it's switching the relay. So it's very sensitive. It can detect the movement in front. Fortunately, the circuit here has a range of 7 centimeter. It will sense an object from 3.5 cm to more than 10 centimeter, depending on the voltage supplied to the circuit board, which is about 7.7 volts to 9 volts. With just some few minor modification, you can extend the supply voltage to 12 volts by changing the value of resistor bias on the LED monitor and the resistor bias on the collector of the output transistor 2N222. So now, this is the 5 volts regulator. the low voltage, low current 5 volts regulator, the 3 volts relay. I'm using only 3 volts relay, or you can use the 5 volts relay, but not a 9 volts relay, because it will drain so much current. The idea is to minimize the current consumption of the entire proximity sensor circuit. The 555 timer IC, the 2SC1815, another 2SC1815. This is the 2N2222 transistor, and the infrared module, the infrared LED. So the circuit for the infrared transmitter is the commonly typed circuit that you can download from the internet, or you can build your own, because it's not so difficult to design an infrared transmitter using the 555 timer IC. So this is the infrared motion detector I bought from a toy store. Unfortunately, after I tested it, it works, but it's only momentarily switched, so it's not useful for continuous operation or continue the infrared sensing for my Raspberry Pi vacuum cleaner robotics project. So that's it for now. By the way, before I close this video, I need to show you the current consumption here. This is the condition where the infrared proximity sensor is not active, or not sensing in infrared, or the reflection from coming out from the infrared transmitter is not reaching the infrared receiver. It consumes about 90 milliamps. Now I put the object in front of it. It consumes about 240 milliamps. That indicates that the relay is active and the LED monitor is on. So, depending on the voltage applied to the circuit, which is about 7.7 volts to 9 volts, the current will also go up. So that's it. Until my next circuit. One last thing, I almost forgot. The oscillation must be 38 kilohertz, between 37.5 and 40 kilohertz, but the sensitivity of the receiver module depends on the 38 kilohertz center frequency. I'm going to show the frequency here. This is the output pin 3 of the 555 timer IC. As you can see here, the frequency counter shows 37.8 kilohertz, which is very close to 38 kilohertz. If you go above 40 kilohertz, the receiver module will not detect the infrared transmitter signal. So it has to be stable between 37.5 and 38 kilohertz. On the scope, here it is. This is a signal from the output pin 3. The output voltage is approximately 8 volts square wave. And about just a cycle of 60 to 70. That's it. We're close now. This is the end of this video. Until my next video clips. Bye.